Okay, on this episode, we're going to continue the amino acids. Last time, we left off with some unique properties of the amino acids, such as the L and D configuration, which is the relative configuration, and the SR, which is the absolute configuration. And I kind of want to continue that a little bit here, specifically the L and D configuration. R and S configuration is determined by the Kohn-Angled Prelog rule. So if you want to look more into that, check that out. But for now, I'm just going to leave the R and S where they were, what we talked about in the last episode, because if I were to talk more about it, it would be more of like an organic chemistry type of deal, which I don't want to get too much off topic. So I'm just going to leave it at that. But L and D configuration is really, really quick. So I did want to go over that. Like I said, L and D, relative configuration, is the configuration of the molecule as a whole. So we can use, it's called the Korn rule to figure out the L and D configuration. So the Korn rule, we have CO, we have R, and we have N. Okay, so I wrote it like that because I want to split it up into its individual groups. So we have CO, we have the R group, which R is just whatever side chain, and then the amine group. Okay, so in that order, if we draw a circle, we would be going counterclockwise. L is counterclockwise. Okay, and if we were to do the same thing, on this one, on this stereoisomer, it would be the opposite direction. If we're following CO to R to N to spell out corn, it would be D, which D just goes in the opposite direction. Okay, so if you ever need to solve for L or D of the amino acids, which they can mix it up in questions, that's how you solve for it. You follow the Korn rule, where you're just going from CO, carboxylic acid group, to R, the substituent, or the side chain, I should say, to N, the amine group. Awesome. So the next thing I want to go over are Zwitter ions. We're going to go to the next page for that. So Zwitter ions, what the heck are those? So a Zwitter ion is just any time an amino acid, specifically a charged amino acid, has two charges that are opposite. So this molecule, this histidine, has a positive charge and a negative charge. That makes it a Zwitter ion. I just wanted to go over that quickly because it is terminology that we need to know, that it's just got a positive, it's just got a negative. They cancel out. Whoops. They cancel out and it's neutral. Okay, cool. But now I want to get more into like, what does ionizable even mean? So in the first amino acid video, I described 7 different amino acids as being ionizable. What does that mean? It means that they could ionize in a couple different ways, and it's depending on if it's deprotonated or protonated. So amino acids can have different forms. They can be in a protonated form, which we see right here. This is the protonated form of aspartic acid. Okay, so when I say protonated, I mean these hydrogen molecules. Okay, hydrogen is considered a proton here. Okay, so the left would be protonated, the right would be deprotonated. As we can see, we are missing a hydrogen. We're missing a hydrogen, so that is deprotonated. So how the heck does it become deprotonated or protonated? Well, it depends on the pH relative to the pKa. Okay, so it says pKr, but we can just think about it as pKa. Okay, pKa is an innate property of the molecules based on their acidity or basicity. Okay, aspartic acid is very acidic, and its protonation state can change depending on the pH. Okay, so I just want to make a little key on the left here. If pKa is less than the pH, it's going to be deprotonated. It's going to be deprotonated if pKa is greater than the pH anytime it's protonated. Okay, and if pKa is equal to pH, it is said to be 50-50 of deprotonated to protonated. Okay. So, that being said, now we know how that works. So anytime a question is comparing pH and pKa, we need to know that relationship in order to understand whether a molecule, in this case amino acids, are protonated or not. Okay. And these are all of our possible ionizable side chains here. We have, this is basic, this is basic, this is basic. These are our unique, these are both polar amino acids. And then up top, glutamic acid, aspartic acid, both acidic. Okay, so I want to talk more about pKa. We already said how it is just an innate property of the molecule. Oftentimes, they'll just give us the pKa. Okay, so if you're wondering how the heck do I solve for the pKa, most of the time, they just give it to us. And something I should note that I didn't know before, actually, is that we don't need to memorize the side chain pKas. We actually do need to memorize the backbone pKas. Those are the same in every amino acid. The carboxylic acid group is around 10 for the pKa, or excuse me, is around 2 for the pKa. It's acidic, so it's going to be small. The amine group is going to be around 10. I'll make that squiggly better. The amine group is around 10. It's basic. Okay. So pKa kind of follows pH. The lower it is, the more acidic it is. The higher it is, the more basic it is. Okay. But in some cases, we will need to solve for the pKa. So how the heck do we do that? And this example is for a basic molecule. So it's different for basic and acidic molecules. But essentially, we're just averaging pKa's of side chains, of substituents. Okay, so we're just finding averages. Okay, and they're saying PI here, which is for isoelectric point. We'll get more into that in the future, but instead of thinking about it as isoelectric point, let's just think about it as pKa. Just think about it as pKa. Okay, so like I said, we're averaging the side chains for basic molecules. For basic amino acids in this case, we're taking the highest pKa's, the most basic pKa's. Okay, so it's going to be the pKa of the side chain and the pKa of the amine group on the backbone. Okay, so we're literally just averaging them. So 12 plus 9 approximately divided by 2, and now the pKa of the entire molecule, the entire amino acid, is 10. Okay, we're doing the same thing with this histidine. We're doing 6 plus around 9. And the final answer is 7.58. Same thing with lysine. Difference between 10 and 9 here. Okay, divided by 2, and we get 9.74. Okay, so for basic, we take the most basic and average them out. And now we're going to do an example of acidic, which you probably guessed it. We're taking the two most acidic groups and averaging them. So the carboxylic acid on the backbone, take that, add it to the side chain pKa, which in this case is acidic because it's aspartic acid, average them 2.7. Backbone, side chain, add them, divide by 2, 3.2. Okay, so that's how we solve for the pKa if we ever need to. Okay, so that's it with ionization. Just remember, just want to reiterate, protonation states, that's a really big one, okay? We need to know this for sure. We'll be asked a bunch of questions on it. This page keeps changing. I'm so sorry for that. But we need to know that. Okay, if it helps to kind of think about it, let's think about the when the pKa is less than the pH, then our molecule has the molecule is acidic relative to the environment. So the environment is basic. Okay, and if we think about our acid-base definitions, bases, or in this case the environment, are electron donors. Okay, so the fact that the environment is electron donating means that our molecule is going to be deprotonated. When the pKa is less than the pH, the environment is more basic, so our molecule is going to have electrons donated to it. Okay, and the opposite is the case for when pKa is above pH, and then pKa equal to pH is our 50-50.